Hello all, welcome back to our lectures. Today we'll be talking about carbohydrate metabolism. Particularly, we'll be looking at the first part of carbohydrate metabolism, which is glycolysis. In the last chapter, we introduced ourselves to intermediary metabolism. And then today we're going to be kicking it off pragmatically. All right, let's take it off from there. But before we do that, I have a nice quote from you. It's from Nelson Mandela. I had him in one of the quotes in the last module as well. He says, the greatest glory in living lies not in never failing, but rising every time we fall. Rising every time we fall. We are not infallible, we're going to fall. But the ability for us to adjust and rise to overcome our challenges is what defines us and what defines our future. All right, let us take it off from there immediately. The metabolism of carbohydrates starts from the mouth. It starts from you eating the food, the solid foods. The foods need to be broken down to the simple part. Remember when we talked about the 3 ways of extraction of foods from nutrient. The first thing we said was that in the first part, the biomolecules are broken down into their building block molecules or into their simpler unit. So carbohydrate, when you eat carbohydrate like in form of starch, in form of cellulose, in form of whatever, first of all, the digestion starts in the mouth when the mouth secretes the salivary amylase. Although amylase is a class of enzymes that actually catalyze all carbohydrate. It just depends on which type now. So salivary amylase actually act on starch and break it down into a mix of dextrins, including disaccharides. Those dextrins could include like some trisaccharide, some tetrasaccharide, and some pentasaccharide and disaccharide, and even a few monosaccharides as well. Now, nothing happens in the stomach. Again, something happens in the small intestine. In the small intestine, the pancreas secretes the pancreatic juice, and one of the content of the pancreatic juice is the pancreatic amylase that does what? That now acts on particularly the disaccharide. You know, when you get to the saccharide, that means you are like one step away from getting them to the monosaccharide or simple sugars, which the body needs to absorb. So pancreatic amylase contains 3 enzymes, sucrase. The sucrase act on, remember the sucrase will act on, the sucrase will act on sucrose, converting it of course into glucose plus fructose. This is what the sucrase does. The sucrase will break this thing down. And then the maltase will act on maltose. Maltose, of course, is a disaccharide. It will act on maltose, converting it to 2 molecules of what? Glucose. So you have 2 molecules, glucose plus glucose. The maltase will break this down. Whereas the lactase itself will act on what? Lactose. Lactose will be broken down to what? Galactose plus glucose. When we studied carbohydrates, this particular disaccharide, we looked at them very extensively, and we also knew the type of bonding that is being hydrolyzed by this amylase. So after breaking down into these building block molecules, monosaccharides or sugars, now they need to be absorbed by the walls of the intestine. The walls of the intestine that actually does this absorption is called the vilus. If it is plural, it is the villi. So glucose, fructose, and galactose will now be absorbed by the walls of what? The villi, and they now enter into the bloodstream. It is inside the bloodstream that they make their ways into the cell, and inside the cell, particularly in the cytoplasm, glycolysis begins to take place. Before we now go into, let us get some important terms that are associated with blood glucose in the body. Now, blood sugar level is the amount of glucose that is present in an individual's blood that is usually expressed in milligrams of 100 ml of blood glucose. When you go to the hospital, one of the common things they do, particularly for adults that have the risk of diabetes, is to check the level of your blood glucose, and it is expressed in milligrams per 100 ml of your blood plasma. Now, it is usually high. Now, after a carbohydrate-rich meal, the level of blood glucose increases, which is normal. You have a lot of blood, you've eaten a heavy starch or something that is carbohydrate rich, it's going to shoot up. The moment it goes up, let's say a few hours after meal, it's going to go up. However, in a normal regulation, if the person is not diabetic, now diabetes is going to stimulate what? The storage of that excess glucose either as glycogen or stimulate it to be broken down, to be taken up by the muscle cells for glycolysis. That means it's going to fall after a time. So what that means, after, if you take the food, after about 1 hour or 2 hours, it's going to be hard. It's going to go up and then return. So let's say after 1 hour, it's going to go up. Then at about 2 hours again, it will begin to go down. And by the time you get to 3 hours, you should have it back to normal. So this becomes like the maximum point. So this should happen in a normal person. So it returns to normal after 2.5 hours. All right. So hypoglycemia, of course, let's now begin to bring other important terms. Hypoglycemia is a condition where someone has lower than normal blood glucose. So if you have a blood glucose that is lower than normal, I think particularly that's about 120 milligram, lower than 120 milligram per 100 ml of blood. Hyperglycemia is a condition whereby you have more than normal of normal blood glucose. And when it is normal, when it is beyond this, some things might actually happen. The kidney might begin to express somewhat glucose, and that can lead to the excretion of sugar or glucose in the urine. So the renal threshold is the blood sugar level at which the sugar is not reabsorbed by the kidney. At a normal renal threshold, the kidney is not going to get them. It will not be expressed in the kidney. However, in a condition whereby the renal threshold has been breached as a result of diabetes or any associated disease, what happens? It will be expressed in the kidney, and the kidney will reabsorb them and excrete them. In that condition, we say it is what? Glucosuria. So glucosuria simply means a condition in which elevated blood glucose levels result in the excretion of glucose in the urine. At that point, it has exceeded the what? Renal threshold. So now, usually, there are most organs metabolize glucose, but we're going to focus our attention into two. Now, the liver regulates the blood glucose level immediately. It gets into the body, because the moment it is absorbed, the food you absorb from the hepatic portal vein goes through the liver. What does the liver do? Now, the liver responds by increasing what? Responds to increase in blood glucose by what? By removing glucose in the bloodstream. How does it do that? It does that principally by converting excess glucose into glycogen or glyceride or triglyceride. So it converts excess glucose into glycogen or triglyceride. So synthesis of glycogen from glucose is called glycogenesis, and that actually happens in the liver. We're going to talk about that by the time we look at the storage mechanisms of carbohydrate. Now, so what it basically does is that it can also, when the blood glucose level is low, it can also convert glycogen back to glucose and also synthesize new glucose molecules from non-carbohydrate substances in a process we call gluconeogenesis. So it depends on the condition of the blood glucose that will trigger what the liver does at that point in time. Now, another organ that also plays an important role in this regulation is the cells. The muscle cells take up glucose, particularly when they are stimulated by insulin through what we call the GLUT4 transporter. It's not part of what we're going to be talking about here. But the muscles will take up this glucose from the blood, therefore reducing the level of glucose. What do they do with it? They quickly do what? Undergo glycolysis or break down the glucose and release ATP and energy, which is now used particularly for muscle cells, particularly in an active skeletal muscle. And like I said, taking up that glucose from the blood, taking up the glucose from the blood by the muscle will also lead to what? The reduction of blood glucose. Now let's get straight to the first reflection. It says, what is the condition in which glucose appears in the urine? I can give you time to look at this and think about it a little bit, but I just talked about it. When the renal threshold is breached, the kidney absorbs what? The kidney absorbs glucose and then excretes it. And at that point in time, we call the condition glucosuria. All right. Now let's talk about glycolysis, which is our subject matter today. We're going to spend time on glycolysis. Glycolysis simply means gly. Gly means glucose. Gly is just glucose. Lysis means breakdown. So glycolysis simply means what? The breakdown of glucose. It occurs in the cytoplasm. It's important to check this, because by the time we begin to talk about citric acid, we know that it occurs in the mitochondria. So, most metabolic pathways are compartmentalized. What it means is that they have to take place where the enzymes of those systems are resident. So, in this case, glycolysis takes place in the cellular cytoplasm. What happens? Glucose, which is 6 carbon unit. Of course, you know the formula of glucose, C6H12O6, is broken down or oxidized catabolically through a series of processes, through a series of 10-step reaction into pyruvate. Pyruvate contains 3 carbons. So that is exactly what. So the enzymatic rearrangement and series of reaction is just to break down glucose that has 6 carbon into 2 3 carbon units of pyruvate. Now, it uses, what happens? It uses ATP. There are 2 steps that use ATP, and it also generates ATP. So it actually uses 2 ATP, generates 4 ATP, so that at the end of the day, we have the net ATP, the net 2 ATP that is generated in glycolysis. Now, the net reaction of glycolysis is glycolysis plus 2 Pi plus 2 ADP plus 2 NAD. Now, what does it produce? In net reaction, you have 2 moles of pyruvate, like I said earlier here. You have 2 moles of ATP produced because it uses 2 and produces 4. You have 2 moles of NADH that continues to the electron transport chain, or that goes to various other alcoholic or lactic acid fermentation. 4 moles of hydrogen ion and water. So, but these 3 will be the important highlight we're going to make. 2 moles of pyruvate that continues its journey to the citric acid, 2 moles of ATP that is used for metabolic energy, and then 2 moles of NADH that finds its way to the electron transport chain and is further oxidized to also generate ATP. So we're going to see what is going on in the next page. Let's look at it. Now, so like I said, ATP is a 10-step enzymatic series of reaction. And now, in most textbooks, they usually say, okay, we're going to divide it into 2. Yeah, we can do that. We can divide it into 2. The first 5 reaction and the last 5 reaction. In fact, the first 5 reaction is conveniently called the investment phase, if you wanna do that. So you see, from reaction 1, I labeled all of them to reaction 5. The reaction 5 is here. So from 1 to 5 here can conveniently be called the investment stage. You invest something. What do you invest particularly? You invest ATP. And here, the last 5 reaction from 6 to 10, we call it what? The payoff. The payoff, where we now get back something from it. Okay, let's see what happens immediately. Let's just see what happens. Now, I have my note here. We're going to be taking down the number of ATP used or generated and the number of NADH. Those are the important things we need to talk about. And like I told you, we're finally going to be arriving with 2 moles of pyruvate. The first reaction, the enzyme hexokinase comes in to transfer. It has 3 phosphate groups. It transfers this phosphate group to carbon number 6. This is the Howard projection of glucose. I decided to open it up into the Fisher projection here, just to make it a little bit clearer. Now, the phosphate group is represented as Pi, as the inorganic phosphate. Remember, the inorganic phosphate is just this, just to let you know, just for convenience of drawing through my software. That is how I represent the Pi as this. So, ATP transfers one of these phosphate group to carbon number 6 to form glucose 6-phosphate. The enzyme that does this is the hexokinase. This reaction is irreversible, and this enzyme is an allosteric enzyme. And we're going to see the importance in regulation. In reaction 2, now look at it now. This is glucose in number 6. This is, remember, if you want to count the number of carbons, you usually start counting from the most oxidized one. So this is 1 to down to 6. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. This is glucose 6-phosphate. Glucose 6-phosphate undergoes isomerization. An isomeric enzyme that is called phosphoglucoisomerase now does what? Changes this glucose. Now changes this glucose 6 to a fructose. Remember, a glucose and fructose are isomers of the other. Glucose is an aldehyde, whereas fructose is a ketone. That's the difference. So what it does is to move this carbonyl carbon from this carbon number 1 to carbon number 2. That's exactly what has happened here. And the enzyme that does this is the what? Phosphoglucoisomerase to form fructose 6-phosphate. Now the next reaction, fructose 6-phosphate will now be converted to fructose 1,6 bisphosphate. Another transfer of high energy phosphate is taking place. Look at what is happening here. ATP comes in again, transfers another phosphate again to carbon number 1. If he puts it in carbon number 1, that is what we call it fructose 1,6 bisphosphate. There is phosphate in carbon number 6 already, we saw here, and another one now in carbon number 1. So the enzyme that does this is a kinase, and this kinase is phosphofructokinase 1. This reaction is irreversible. Let me just mark these reactions. This reaction is irreversible, and this enzyme is an allosteric enzyme playing an important role in regulation of glycolysis. In the next reaction, what is happening? The next reaction is branching to the fourth reaction. Now remember, this is cis-carbon. An enzyme, an aldolase enzyme is an enzyme that breaks. It just comes to break this carbon into two. It's like a machete. So this machete of aldolase will come in and do, well, let's count 1, 2, 3, and break this from here. So 1, 2, 3, 1, 2, 3. So it comes and breaks fructose 1,6 bisphosphate into 3 carbon units. These 3 carbon units are, number 1, the dihydroacetone phosphate, and then the glycerate phosphate. Look at what happens here. The difference is here now. It's very clear. From this side, this is an aldehyde, right? This is a ketone. This carbon is a ketone. If you break this from here, what you have here is a ketone. And dihydroacetone phosphate is what? Remember, this is a ketone. This is an isomer of this as well. So this is a ketone, whereas glycerate phosphate is an aldehyde, because this one is at this. So this is an aldehyde. This is a ketone. So this guy and these guys are isomers of each other. Now what happens? The reaction of glycolysis does not support dihydroacetone phosphate anymore. What happens is that the rest of this dihydroacetone phosphate that was produced will now quickly be isomerized to glycerate phosphate. And the enzyme that does this is another isomerase. It is the triose phosphate isomerase that converts all of the dihydroacetone phosphate to glycerate phosphate. This is the first 5 stages of this reaction. What has happened here now? Let's take note what has happened. 2 ATP molecules has been used. Here, 1 molecule was used. Here, another. So we've used 2 ATP molecules actually. Or maybe let me use a different color to do this. So we've used 2 ATP molecules has been used in this phase of reaction. We've not generated any NADH. Let's now go to the second phase. This is that's why we call it investment. So you can say negative. Negative. It's a negative because it's you use this, so negative 2 ATP. Good. Now let's go to the next phase, which is the payoff phase. What is happening? In the first reaction of the payoff phase, let's see what is happening there. In the first reaction of the payoff phase, which is reaction 6, glycerate phosphate, remember now, when this is now converted to this, it now becomes 2 molecules. Because there are 2 molecules of 3 carbon unit of dihydroacetone phosphate and glycerate phosphate. So when this is isomerized complete to this, what it means is that at this point, everything is now multiplied by 2. So we have 2 glyceride there. If we have 2 glyceride, everything happening here now will be doubling it by 2. So what that simply means is that 2 molecules of glyceride will each individually be converted to what? Will be converted to 1,3-biphosphoglycerate. What has happened here is 1. A phosphate group comes and become attached to what? To carbon number 1. That's exactly so. A phosphate group, it has one here already. Another one was attached here, and the enzyme that does this is glycerate phosphate dehydrogenase. Most dehydrogenase enzymes are NAD plus dependent. What is happening here is that the NAD plus, which is a coenzyme, has come in to do what? That's what it's doing here. It has come in to do what? To accept 2 hydrogens here to become what? NADH plus NADH plus H plus. So we'll form one more. So we'll form an NADH here. So since there are 2 of them reacting here, we're going to be having 2 moles of NADH at this point. That's exactly what we have at this point. So we can write it down. So in reaction number 6, we now produced 2 moles of NADH. That's what we've just gotten in this reaction. There are 2 moles of NADH in step 6 of this reaction. Okay, we now go to the next one. In the next reaction, what is happening there? It formed, remember, when this thing happens, transfers another phosphate to this, it now forms 1,3-bisphosphoglycerate. Now 1,3-bisphosphoglycerate has a phosphate group in carbon number 1 and carbon number 3. Now quickly, what happens? Step 7 is important. Step 7 is called substrate level phosphorylation. This is the first step that generates ATP. This type of phosphorylation is different from what happens in the mitochondria, which is an aerobic process. This is an anaerobic process. No oxygen is involved. This type of phosphorylation is called substrate level phosphorylation. So what is happening here is that 2 molecules of this, each individually, is converted to 3-phosphoglycerate. What it does is that one of these phosphate group was transferred to ADP. ADP accepts it to become a triphosphate. And then this ATP, of course, you know what it's used for is a metabolic energy. And it is converted to 3-phosphoglycerate. So having lost that, it becomes 3-phosphoglycerate. 3-phosphoglycerate, look at what happens again. 3-phosphoglycerate will now be converted to 2-phosphoglycerate. Look at what is happening. The phosphate group in carbon number 3 was now transferred in carbon number 2. And the enzyme that does this is an isomerase. This isomerase is called phosphoglycerate mutase. A phosphoglycerate mutase transfers this phosphate group from carbon number 2 to carbon number 3. In the next reaction, an enzyme, the NLS, comes in to remove 1 mole of water. NLS is coming to remove 1 mole of water. What is happening now? If you remove this OH group and if you remove OH and 1 H from here, that's 1 mole of water, and introduce a double bond. And when you introduce this double bond, it forms an enol. The product forms is now called phosphoenol pyruvate. It's called an enol because it now has a double bond. And the enzyme that does this, like I said, is called NLS. And then this is the 9th reaction. And now, which is the penultimate. We're now going to the last reaction below the list. In the last reaction, the phosphoenol pyruvate. Again, remember, everything happening here is into double. 2 molecules of phosphoenol pyruvate each is now converted to pyruvate. And in this case, again, look at what is happening. The phosphate group in this carbon number 2 is now transferred to ADP to form ATP. Adenosine triphosphate accepts 1 phosphate group to become adenosine triphosphate. And then phosphate group is now being lost from here, and the phosphoenol pyruvate itself is now converted to pyruvate. And this is the last reaction. So the last reaction of this yields 2 mole of pyruvates in the payoff stage of glycolysis. Now, what has happened in this payoff stage? Let's take stock again and take some note. Here, 2 ATP. Remember, I told you everything happening is in 2. So you can say 2 ATP was produced there and another 2 ATP for. So here we now have, because it was produced, it's a positive. So it's going to be plus 2 plus 2, 4 ATPs were produced. And if you want to know the overall, minus 2 ATP plus 4 ATP give us plus 2 ATP is generated in glycolysis. So 2 ATP is generated in glycolysis, 2 NADH is generated as well. This is the glycolytic pathway. And then we now go to the next thing. Let's now talk about a little bit of the substrate level phosphorylation. I told you, step 7 and step 10 generate ATP in the cytoplasm. The generation of ATP from substrate by phosphate transfer in the cytoplasm is called substrate level phosphorylation. It is different from the one that happens in the mitochondria, that is an aerobic process. This is typically an anaerobic process because no oxygen is involved. Step 7, 1,3-bisphosphoglycerate was converted to 3-phosphoglycerate, and the enzyme that does this is the phosphoglycerate kinase. The kinase enzymes are enzymes that transfers phosphate group. Again, in step 10, phosphoenol pyruvate is converted to pyruvate by the enzyme pyruvate kinase. I forgot to mention, now the pyruvate kinase is an important regulatory enzyme at this point, which we're going to see how important it is as well. It's an important regulatory enzyme, and I remember the other ones I did was I put an asterisk there. So the 3 important regulatory enzymes here is the hexokinase, the phosphofructokinase, and the pyruvate kinase. Now, having talked about substrate level phosphorylation, just remember, we're going to be comparing this with the type of phosphorylation we see in the mitochondria, involving the coupling of electron transport chain with oxidative phosphorylation. We say the name oxidative because it involves oxygen, but this is called substrate level. It is produced from transfer of phosphate group from one substrate to another. All right, so let's move to the next thing. How is glycolysis regulated? Glycolysis is regulated in 3 ways. Remember, in enzyme, we looked at what we call the feedback. A feedback inhibition is whereby a product comes back to inhibit the enzyme that leads to its synthesis. There is also the feed forward means opposite of feedback. So it's like a positive regulation. It's a kind of motivation or activation of what? A pathway by a product after it has been synthesized. It goes to what? It goes to activate a future enzyme in that pathway. We're going to see that. And then allosteric regulation, of course, we talked about this. Allosteric enzymes have different binding sites, whereby different modulators can bind and either activate or inhibit them. Now, glycolysis, the main aim of glycolysis, like we saw, are two things. Like we said, it leads to the generation of ATP, which is used for energy, and it also leads to the generation of NADH. Now, this NADH is used in generation of energy in the electron transport chain. Okay, so we'll now go back to the regulation. So when ATP level is low, the AMP, which is adenosine monophosphate and adenosine diphosphate, are usually high, and vice versa. So when ATP level is low, the AMP and ADP levels are high. It signifies that what? That the energy state is low. In a low energy state, glycolysis needs to take place because more ATP need to produce. Because glycolysis leads to, like we said, it leads to what? The generation of an extra 2 ATP overall. So it needs to be working. Now, in opposite direction, like I said, vice versa, when ATP is very high, the level of AMP and ADP will be low. What it simply says is that the energy state is what? Is high. And such high energy state is going to slow glycolysis down. What it means is that you already have enough ATP, so no need for glycolysis to take place to generate more ATP. So having said that, let's look at what is happening. So I broke it down. If you look at this reaction, this is a summary of what happens in glycolysis. Remember, glucose goes to glucose 6-phosphate. Glucose 6-phosphate goes to fructose 6-phosphate. Fructose 6-phosphate, remember the hexokinase enzyme does this. Fructose 6-phosphate goes to what? Fructose 1,6-bisphosphate. The enzyme that does this is phosphofructokinase 1. We usually call it phosphocructose kinase 1. I'm going to tell you the reason why that happens. We usually call it phosphofructokinase 1. Then, after that, a series of reactions will take place to convert this to phosphoenol pyruvate, which is the second to the last reaction. Phosphoenol pyruvate will convert it to pyruvate. The enzyme that does this is pyruvate kinase. I have all the keys here. Now, the pluses means activation, the negative means inhibition. Let's see what is happening in regulation. Now, in this loop is called the negative feedback loop. This is an inhibition. Glucose 6-phosphate is the first product of glycolysis and produced directly from glucose. What happens is that in high concentration of glucose 6-phosphate, it goes to what? Inhibit hexokinase and tell it, okay, there is enough ATP, no need to keep producing. This is a feedback control. Now let's see what happens again. Now in phosphofructokinase 1, which is the third reaction and the third enzyme happening in glycolysis, look at what happens here. Now, when the energy level is low, like I said there, when the energy level is low, AMP and ADP wants glycolysis to take place. They will go and bind on this enzyme. So this is allosteric inhibition. This is allosteric. This is allosteric inhibition. When it is low, they will go and bind and facilitate the making or facilitate the speeding up of glycolysis. Now, however, what happens when it is very high? When ATP is very high, ATP itself is a product of glycolysis. So it goes to bind phosphofructokinase to say slow down. So ATP is an inhibitor with citrate. Citrate is a product in citric acid cycle or tricarboxylic acid cycle. We're going to talk about that much later in TCA. So this is a kind of negative feedback because it comes actually to bind this guy and say slow down. The same thing with ATP because ATP comes here as well. ATP is generated here and ATP is also generated at this process and here too. ATP is also generated here. So it also comes from here and say, okay, take it easy. We want this reaction to stop. This is also both negative feedback and allosteric modulation. The same thing also happens in this one. From phosphoenol pyruvate to, remember I said ATP is generated here. So, because this is the last reaction, ATP is generated here. Now again, the ATP that is also generated here and the one that is maybe generated in citric acid cycle 2 comes to also inhibit pyruvate kinase when the energy level is very high. And so, okay, slow down glycolysis, will have enough ATP. And then, however, when it is very low, AMP and ADP will bind to this guy and trigger the continuation of glycolysis. Now, look at what happens in the feed-forward, which is very interesting. A feed-forward reaction, remember this is a negative feedback, this gold bar. Look at fructose 1,6-bisphosphate is the product of this reaction of fructose or phosphofructokinase 1. Now, what it does is that fructose 1,6-bisphosphate goes to bind for pyruvate kinase to promote glycolysis. This is a typical example of a positive control, or what we call a feed-forward control, which is an activation control. So this is a simple illustration of the enzymatic control of glycolysis. Let's now move to the next thing. Reflection 2. It says, which of the following is the end product of glycolysis? You should have known. Glycolysis results in the generation of 2 moles of pyruvate. That becomes the answer. Again, another question. It says, reflection 3. Where does glycolysis take place? I said this. Glycolysis takes place not in the mitochondria. It takes place in the cytoplasm. All right. It is compartmentalized at the cytoplasm. All right. Let's move to the next thing. Now, pyruvate has 3 metabolic fates. After production of pyruvate, what else? What happens? Does it just go off? No, it doesn't disappear magically. It has 3 metabolic fates. The 3 metabolic fates has been summarized in this structure. This is our pyruvate. Pyruvate can be converted to 3 ways. Let's start. The first 2 ways we're going to illustrate to the left and to the right is the anaerobic. Anaerobic process means it is not taking place in the mitochondria. There is no oxygen. Now, in some prokaryotic organisms and some bacteria, pyruvate is converted to ethanol in what we call the alcoholic fermentation. So this is alcohol fermentation. In alcohol fermentation, the enzyme alcohol dehydrogenase comes and converts pyruvate to ethanol. In fact, this has a first intermediate. The first intermediate is, remember, alcohol has 2 carbons. So the first reaction actually is decarboxylation. Is pyruvate decarboxylate comes to break this carbon to form acetaldehyde. Then acetaldehyde is now being converted by the enzyme alcohol dehydrogenase to ethanol. So the enzyme that acts at this point, okay, let's pick number 1. The enzyme that acts in this first alcoholic fermentation is alcohol dehydrogenase. So this is called alcoholic fermentation, and it occurs in bacteria and some other prokaryotic organisms. Now, in the second anaerobic process, takes place even in multicellular organisms like the mammals. In the muscle, pyruvate is converted to lactate. Here, this is a quick switch of trying to regenerate NADH. In fact, the ultimate aim of all this fermentation process is the regeneration of NADH, so that this NADH will go back to glycolysis, so that glycolysis does not grind to a halt. So, if you look at this again, it regenerated NADH again. Now, in this process, what is happening? Glycolysis is now pyruvate is converted to lactate by the enzyme. The enzyme involved here is what? Is the lactate dehydrogenase. And this is called lactic acid fermentation. So this is lactic acid fermentation. And the enzyme that does this job here, is lactate dehydrogenase. Oh, that does not fit into my right. I'm going to dehydrogenase. Yes, lactate dehydrogenase is what does this job at this point in time. And like I said, this happens in the muscle, particularly in athletes that are running. They need a quick burst of energy. Glycolysis provides that immediate burst of ATP that is needed for sprinters who run short distance runners. That has to involve speed. However, the accumulation of lactate will lead to muscle strain, because lactate itself is an acid. You know, this is the conjugate base of the acid. So it's an acid. If you put H here, that means it can ionize. And when there's a lot of this acid accumulating in the muscle, it leads to muscle pain and cramps that is characteristics in in sprinters as well. Now that is the second pathway of, remember these two pathways are anaerobic without oxygen, the one to the left and the one to the right. Now the ultimate one that generates a lot of energy is the aerobic process that needs what? Oxygen. There's oxygen here involved, and this is the third fate of pyruvate. What happens here? Pyruvate is converted. Now look, if you look at the other reaction here, the NADH that was generated in glycolysis, like I said, was, this is the reduced form, was reoxidized. That's exactly what happened in this place. The same thing happens here as well. It was reoxidized. If you look at it, this guy, this 2 hydrogen was now transferred to this guy to make it OH. So lactate is the reduced form of pyruvate. That is what you can easily put forward. The same thing is also happening here. Now in this case, something different is happening. NADH is used to oxidize pyruvate to acetyl-CoA, and the enzyme that plays this important role is called, remember this is an aerobic process. The enzyme in this number 3 is the pyruvate dehydrogenase. We're going to see it in more detail in the next slide. This is pyruvate dehydrogenase. And what actually happens here is that it involves a decarboxylation. What happens here? It breaks one of these carbon off as COO2, and then coenzyme A comes in to attach this CoH. A CoH comes in here, is not represented, but I'm going to show you the other one, to attach the coenzyme A to activate this molecule to form acetyl-CoA. Acetyl-CoA is active, and what happens again? It can now continue with carboxylic acid cycle. Now, it's important to know this. Whereas these two anaerobic processes still take place in the cytoplasm, the decarboxylation of pyruvate to acetyl-CoA is what? Taking place in the mitochondria. So this reaction is aerobic. Aerobic means with oxygen, and that with oxygen is taking place in the mitochondria. All right? And so, like I said earlier, all these processes result to the regeneration of NAD+. However, this does not regenerate NAD+ here. It now has to enter the electron transport chain, and where it is now going to be regenerating a lot of NAD+ that will now go back to facilitate glycolysis. So like I said, pyruvate oxidation to acetyl-CoA occurs in the mitochondria under aerobic conditions in the presence of oxygen. Most of this acetyl-CoA will completely be oxidized to carbon dioxide in the citric acid cycle. So the acetyl-CoA will now enter the citric acid cycle or the tricarboxylic acid cycle and now be broken down to carbon dioxide completely. And it is in the citric acid cycle and the electron transport chain that, or rather, it is in the electron transport chain that the NAD+ that is generated is regenerated. So the NAD+ is generated when NADH from both the citric acid cycle and other pathways like the beta oxidation are now doing what? Are now reoxidized by the transfer of electron to oxygen. So it now regenerates NAD+, which now goes back to make sure that glycolysis continues. And then some of the acetyl-CoA will now serve also as a starting material in the biosynthesis of fatty acid. The starting material for the synthesis of fatty acid is acetyl-CoA. So it also acts as a starting material. So the enzyme, to summarize what happens is that pyruvate itself, CoH comes in here. Now this decarboxylation occurs here, and then to remove carbon dioxide, the CoH now, coenzyme, will now be attached to this through the sulfhydryl group to this place to form acetyl-CoA. And the enzyme that does this is the pyruvate dehydrogenase complex. It's a big complex enzyme that involves the use of so many coenzymes like magnesium ion, thiamine pyrophosphate, flavinadenine dinucleotide, and lipoic acid. But we're not going to be talking about those. The main thing here, just know that the enzyme that does this is the pyruvate dehydrogenase complex that involves the carboxylation and the transfer of the coenzyme A to acetyl group to form the acetyl-CoA. And this is what proceeds with the citric acid cycle. All right. We now go to the last part of this lecture. Perfect timing. Reflection 4 says the 3 fates of pyruvate are, remember there is one aerobic fate involving oxygen and there are 2 anaerobic fates. We're going to look at them. It says acetyl-CoA, ethanol, and lactate. the three fates of pyruvate. So let's see. There is acetyl-CoA, which is aerobic, yes, and there is ethanol, anaerobic, and this. Let's look at other options. So what you need to know is to arrange it correctly. The only aerobic one is what? Acetyl-CoA. Just remember that. Acetyl-CoA is aerobic. And then the two anaerobic ones, you can put whichever one you want. So if you start with any one, just make sure that the one that matches the answer. So you can have acetyl-CoA, ethanol, and lactate. So let's see the one that will be correct. It says lactate, this can be this one. It can be this one. It can be this one because ethanol cannot be here. So it has to be number 1. It has to be number 1. So aerobic is acetyl-CoA. Then the anaerobic will be ethanol is anaerobic. And then another anaerobic is also lactate. So number 1 is the correct answer. And having said that, we've come to the end of this lecture today. Thank you for listening. Bye at this point.